Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over electron affinity and why nitrogen has an unexpected electroaffinity given your understanding of the trends on the periodic table. So let's get into this. So as you may have learned in your classes, there are trends in the periodic table: ionization energy trends, electron affinity trends, size trends, and all that stuff. So I'm going to focus in on electron affinity. Electron affinity. And so what do we mean by electron affinity? That's the first thing we need to understand. And what we mean by electron affinity is the change in the energy of a neutral atom when you add an electron to that atom. Okay, so this is a measure of basically how much an atom would like to have an electron, if we could put it in the anthropomorphic terms. But basically, it's due to the stability, or a measure of the stability of the atom, and basically how easy it is to add an electron to an atom, a neutral atom. So it's, in a way, you could think of it in terms of being the opposite of electron ionization energy. That's what I mean. Sorry. So ionization energy, again, very similar to electron affinity, is the energy change of an atom when you remove an electron. It's the energy needed to remove an electron. Well, how much energy is it going to take? Ionization energies are always positive. Why? Because it always takes energy to remove an electron. Why is this? You have to think of it in terms of the stability, or the overall potential energy change in an atom, right? So electrons, you have these negative particles, electrons, and you have the positive nucleus, right? So the positive nucleus is going to be attracted to the negative electron. Negative electron is going to be attracted to the positive nucleus. So they're going to be attracted to each other. So according to Coulomb's law, right? So the amount of force, or the energy between two charged particles, is going to depend on their distance apart and how large the particles are, how large the charge on the particles are, right? So for oppositely charged particles, your potential energy between the two particles is going to be lower as they get closer together. And so lower energy means more stable, right? So everything is seeking low energy. So if you can get that lower energy, if you can get closer to the nucleus, then that's going to be lower energy. There's, of course, a limit to that. So if they get too close, potential energy can increase. So there's a happy medium. So, but the take home of this is that you're trying to get to low energy. When you're removing an electron from an atom, you're increasing the potential energy, right? Because you're increasing the distance between them. That's going to increase potential energy, right? So increasing the potential energy of the atom means that energy was put in to do that. And so you're going to get a positive value for the ionization energy. Well, for electron affinity, it's the exact opposite, right? Instead of trying to remove an electron from a neutral atom, you're trying to put an electron into a neutral atom. So here, you're taking an electron and you're putting the electron into the neutral atom instead of taking it out. And so we're looking at, okay, is that going to be a negative, or is that going to be a positive, or is it going to be zero, right? So the same thing. If I'm putting electrons into the atom, and the atom has a high affinity for electrons, it wants the electrons. So meaning that if I give the electron to the atom and the atom readily accepts it, well, there's going to be a lowering of the potential energy. And that lowering of the potential energy is going to result in a change in the energy of the atom by a negative, right? So this is why, in large part, your electron affinities are going to be negative, because that's showing that those atoms have a high affinity or a relatively high affinity for accepting electrons, because that's going to lead to stability. And the stability, remember, is related to a lowering of the potential energy. So if you're lowering potential energy, that means the atom as a whole is losing that energy. So losing energy is negative value. So, but that's not always the case. Sometimes it's going to take energy to put those electrons in. So if you get a positive value, that sort of indicates that the atom really doesn't want the electron, or it's a destabilization of the atom. And so that's kind of an overview of electron affinity and how it relates to energy changes and ionization energy. So, so the question here that we're dealing with is, it says, explain, well, it's over here, explain why the electron affinity of nitrogen is approximately 0. It's a little bit higher than 0, while the elements on either side, carbon and oxygen, have a substantial electron affinities. And so to answer this question, we have to look at the electron configuration, as well as other things like the Z effective, or the effective nuclear charge felt by the electrons around the nucleus. So let's look at these in turn. So here, these are the the electron affinities of the respective atoms that we are being asked to deal with. So here we have carbon. It has a negative 122. This is kilojoules per mole. So this means that if by adding an electron to the neutral carbon atom, it releases 122 kilojoules of energy per mole. So this has a release of energy. So therefore, this indicates that the overall energy of the carbon atom is going to decrease, thus making it more stable. Nitrogen has approximately 0, a little bit higher than 0, right? So this means that no energy is released, or in some ways, if it's positive, then you actually have to give energy to get the nitrogen to accept the electron. So this is going to take energy to make the nitrogen accept the electron. So this indicates that to some extent, maybe to a slight extent, by adding an electron, it destabilizes the atom a little bit. So since the energy is being taken in, or it requires energy to make the nitrogen to take the electron. And then here we have oxygen as a negative 141 kilojoules per mole. And again, it's negative. So in this case, by adding the electron to the atom, it's going to have it's going to be stabilizing effect. So it's going to be more stable. And so this has a higher electron affinity. So again, I think affinity means you have how should I say, a leaning towards, right? So if I have an affinity for electrons, I lean towards taking electrons, right? So you can see that oxygen here and carbon here have an affinity for electrons, a relatively high affinity for electrons, definitely compared to nitrogen, right? And so you can see that oxygen has a higher electron affinity than carbon. So you can see that going this way, generally speaking, the trend is the electron affinity increases going this way, okay? But what's going on here, that's the question. Why does nitrogen not fit the pattern here? And so part of the answer is looking at the electron configurations. So if you look at the electron configurations, they all have the 1s and the 2s filled. So there's no difference there, right? But when you get to the 2p sublevel, there you see a difference. And the thing we have to keep in mind is that having a full half shell or half sublevel or having a full sublevel is more stable than having anything in between, right? So here you can see that carbon doesn't have a half full shell, but it only needs one electron. If carbon gains one electron, then it's going to have a half full sublevel, and that's going to have a stabilizing effect. So that's going to be a more stable situation than just having two electrons in the sublevel here. So adding an electron to here to carbon will then give it a half shell or a half full shell, and that's going to be more stabilizing, and therefore you see that it has a negative electron affinity. Okay, over here, nitrogen already has a half full 2p sublevel, so by adding the electron here, you're disrupting the stability for a particular reason. One reason is notice that if I put another electron in here, I now have to pair up the electrons in one of the orbitals here. So by adding an electron here, I have to pair these up, and there's going to be repulsion forces between the electrons. So that repulsion forces, again, if we think in terms of the Coulomb's law, like charges, two like charges, if they get close together, if you decrease the distance between them, that actually increases the potential energy because they have the same charge. They want to repel each other. So that's going to increase potential energy by putting them together. We don't want the increase in potential energy. So that increase in the potential energy due to the repelling forces when you add another electron into one of these orbitals, that's going to offset the electron affinity that you would normally have. So that's going to give you a zero or a slightly positive electron affinity because of that repelling force, right? Here you have an empty p orbital, so when you put the electron into the empty p orbital, you don't get that repelling force, so there's no increase in the potential energy, and so this is now going to be stable as having a half shell. Here you would end up having repelling forces. Now, here we have oxygen. So oxygen already has a paired electrons, right? So what's the deal here? Because the same argument can be applied here as here. When I put in an electron here, I've got to pair it up. So that's going to have repelling forces, right? So why don't I have the same thing here with oxygen as I do with nitrogen? That's a great question. And the reason is we got to bring in another factor, and that's the effective nuclear charge that is felt by the electrons. So as you go across, so carbon, nitrogen, oxygen, this is going across the periodic table, right? As you go across this way on the periodic table, what happens to nuclear charge? Well, each time you go from left to right, every time you go over to the next group, you're adding one proton to the nucleus. Well, that's increasing the nuclear charge, right? So here, the increase in the nuclear charge is going to offset the repelling forces for oxygen here. So you don't get the benefit of filling up your whatchamacallit, the sublevel here, right? So we don't have that stabilizing effect. but you do have the repelling forces. So if I add another electron here, I'm going to have repelling forces that increase the potential energy due to those repelling forces. But because I'm increasing the effective nuclear charge here, the effective nuclear charge is great enough to offset the repelling forces that you gain by adding another electron. So remember, the electron that you're adding here is a valence electron. You're adding it to the same energy level, right? So you're not adding any core electrons here. These are staying in the valence shell. So you're going to get some repelling forces, but the overall increase in the effective nuclear charge is enough to offset that. So the electron affinity is going to be greater for oxygen due to that higher electron. I'm sorry, due to the higher effective nuclear charge. So the attractive force of the nucleus is going to be great enough where adding the electron is going to have an overall stabilizing effect. And so it's going to be the affinity, the electron affinity for adding another electron to oxygen is going to be greater. So it's going to be a negative. So that explains why you see this difference in carbon, nitrogen, oxygen in the trend of electron affinities in the periodic table, but in particular between these three. So again, you got to keep in mind that anytime that you add an electron that is going to make a half full shell, or if you add an electron that makes a full shell, that's going to have a stabilizing effect on the atom. The atom is going to want to be more stable. That's going to lower the potential energy. And so that's going to have a negative value. You're going to release energy. So the electron affinities are going to be negative. So they're going to have greater electron affinities. But if you already have a full shell, right, or if you already have a half full shell, adding an electron to that is the electron affinity for that is not going to be good. The energy that's released is not going to be very high, or it's going to require energy to add that electron. And again, that's because you have extra stability when you have either a half full sublevel or a full sublevel. Okay, and so that is the answer to the question, or at least as complete of an answer that I can give at this particular moment. So hopefully that helps clarify why you have nitrogen having either zero or a higher or a positive electron affinity, or what is a lower electron affinity versus the two atoms on the side, or the two elements on the side of nitrogen, carbon, oxygen, and carbon. So that's it for this video. If you enjoyed this video, if this helped you understand this question or this topic, then please by all means like the video, share the video, hit that like button over there somewhere. Also, make sure you subscribe to the channel. Help me out here. Also, click that notification bell. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question, or if you have a particular problem you need help with, or if you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.